All right, you're on the air. So
Hi, Mom.
these are, like I said, these are advanced factor label techniques. Well, that's what you might call it, I guess. We'll call it advanced factor label techniques. Now, it's really the same thing. It's just dealing with a few more complex types of problems and how we can do that. First of all, I'm just going to call this one using density and speed as a conversion factor, okay, or as conversion factors. And I mentioned this before, but I just want to show you examples. You can use any kind of ratio you can use as a conversion factor. Any kind of ratio. So densities and speeds are ratios. Let's try a density. We could say like, and I think you kind of saw one a little bit like this on one of the sheets that you did already. Let's say, what is the mass of 1.0 gallons of liquid mercury? And they would give you in this problem the density of liquid mercury. So the density of mercury symbol is Hg, so that's what that little Hg means there, is 13.5 grams per milliliter. Now, usually density is going to be given to you in grams per cubic centimeter, but a cubic centimeter is a milliliter, all right? And in this case, it's liquid, so it's cool to use milliliters. Right, and this is what you'd be given. Then you've got to be given something else too. There's another conversion that I would give you here, and that is from gallons to liters or to milliliters. In this case, I'm going to give you this. 1 gallon is 3.78 liters. And that's it. Now, remember, you don't want to start with a conversion factor. Don't start with the conversion factor, start with the quantity. So I look up here, and what do I start with? 1 gallon, right. So I'm looking for the quantity that's not a ratio, and in this case it's 1 gallon, and I'm going to start with that. And that tells me automatically that I want gallons in the denominator here because I want to cancel gallons out, right? So now I'm looking up here and I'm thinking, what do I have? By the way, I've already used gallons, so I'm going to cross that out. I've got this thing, right? So I can write 1 gallon and 3.78 liters. Okay. Now I've got a problem though, because it's true, I've just canceled out gallons and now I have liters. If I stop right here, I have 3.78 liters. Problem is, I don't see liters anywhere in my other conversion factor up here. I see milliliters, right? Not a big problem. I know how many milliliters are in a liter, so I'm going to write 1,000 milliliters over liter. And what I'm doing here now is I'm canceling liters, and I'm getting milliliters. And then finally, I can use the density to get the mass of the liquid mercury, 13.5 grams in 1 milliliter. Now, I don't really want to leave this in grams. Let's say, I should have said here the mass in, let's go ahead and say the mass in pounds. How about that? So I'm not done here. I need to know how many grams in a pound. Does anybody remember? About 454 grams in 1 pound. So now I need to do that conversion. So it's 1 pound over 454 grams. Do that calculation with the Alright, so it's 1, hang on, 1 times 3.78 times 1,000 times 13.5 13.5 divided by 454. What's that? Why what?
Why are we multiplying by 160 or 116?
Where?
Hey,
That's
116.
1 pound. That says 1 pound.
Oh,
Sorry.
okay.
Yeah.
Sorry.
112 pounds. I only have 2 sig figs though, so I'm going to write 1.1 times 10 squared pounds. So a gallon jug of liquid mercury is 112 pounds. 13.5 grams per milliliter. 1 cubic centimeter of that stuff weighs 13.5 grams. All right? So that's how we can use a density as a conversion factor. The density was right here. Notice what density does for us. It converts for us from a volume to a mass. So if you're ever faced with a problem where there's a volume and a mass, you should be thinking right away, density. Yes? Yeah, I'm going to give you, in this, let's look at this problem as an example. In this problem, you would have been given this, this, and this. Okay? The only thing you wouldn't have been given is this one, because you're supposed to know how many milliliters are in a liter. So anything within the metric system or within the SI system you should know. But this other stuff like English system conversions, I would give you. Going between metric units, I would give you. I'd even give you something within the English system like quarts per gallon. I would give you that. Now let's look at using a speed. So let's say how long does it take for light to travel, let's say 1,000 miles. Alright, so this is pretty simple. How long does it take for light to go 1,000 miles? Well, I need the speed of light, right? The speed of light has a symbol. It's called c. That's the symbol for the speed of light. And 3.0 times 10 to the 8th meters per second we'll use. Now I can see when I'm looking at this problem, I see there's another conversion I'm going to need. Because here I have miles, here I have meters. And of course it says how long. Let's say how long in, yeah, we'll just leave it in seconds. Keep it simple. But I know I'm going to need a conversion between miles and meters at some point. So I would give you this on the test. I would tell you something like this: 1.602 kilometers per mile. I think that's right. Is it? Or is it 609? You guys have your conversion sheets? 609? Yeah. All right, we'll go with that. Now, what am I going to start with? I am not going to start with the speed because that's a ratio. And I'm not going to start with this conversion between kilometers and miles. Instead, I'm going to just start with 1,000 miles. MI is a symbol for miles, not M. M is meters. I want miles in the denominator because I'm going to cancel it out. And that means I'm going to go ahead and I'm going to use this conversion factor. And it's 1.609 kilometers in 1 mile. That cancels miles. What do I want to do next? I know I want km down here. Yes, Mike? 1,000 meters, 1 kilometer. That cancels out kilometers, leaves me with meters, and my final step is to use the speed, 1 second over 3.0 times 10 to the 8th meters. That'll give me the time in seconds that it takes to go 1,000 miles. So let's see what it is. 1,000 times 1.609 times 1,000 divided by 3, using my little double E button here, to the 8th.
Why did you do 1,000 times 1.609 times 1,000?
Because I've got 1,000 right here,
Oh,
times 1.609 times 1,000, and then divided by 3. So it's 0.0054. I've got, excuse me, 2 sig figs because of my speed of light. 0.0054 seconds, which is 5.4 milliseconds. To go 1,000 miles, light takes 5.4 milliseconds. Yes?
Does it matter when you divide all of that by,
No.
you can just put it in the middle?
Yeah, I could say, I could have typed in 1,000 divided by 3 times 10 to the 8th times 1.609 times 1,000. The order doesn't matter. As long as it's all multiplication and division, the order doesn't matter at all. If you got some addition in there, then you do that first, right? Or some subtraction, then you do that step first. All right, questions about those two? Using speed or... Now, by the way, speed then is a conversion between distance and time. So if you've got a length and a time, or you've given length and asked for time, or you're given time and asked for length, then you're looking for a speed, right? Just to emphasize the point that you can use whatever, any ratio can be used as a conversion factor. Okay? It could be a rate. Maybe it's gallons per minute that are coming out of the, at the gas station, coming out of the pump. Gallons per minute. That's a ratio. You could use that as a conversion factor. So, the next more advanced type of problem is converting cubic units. Now this is lots of fun. And here's how it works. So a question like this might be something like this. How many cubic centimeters are in 1.0 cubic inches? So how many cubic centimeters are in a cubic inch? And you would be given this. But the answer to this question is not 2.54. Right? What's that? The cube of 2.54. See, here's the thing. If you think about a cubic inch, right? What we're saying here, if 2.54 centimeters is a cubic inch, that means this is 2.54 centimeters on this side, right? Well, if you want to know the cubic, if you want to know the volume, and this is a cube, then you got 2.54, 2.54, 2.54, right? So here's what you do. You start with 1.0 cubic inches. Now this is how it's going to work every time you're dealing with cubic units. Chances are you don't know the cubic conversion. So in other words, I don't know how many cubic centimeters are in a cubic inch, right? But I'm given 2.54 centimeters equals 1 inch. So here's what you do. You write the linear conversion. Like that. All right? Now you can do it two ways. You can either write the linear version 3 times. All right? Because see, what would that do? Well, look at, what is this? This is inches cubed. That means inches times inches times inches. That means I have 3 inch units to cancel out. Right? So here we go. One of them's gone. Another one's gone. Another one's gone. And it means I end up with centimeters times centimeters times centimeters, or centimeters cubed in my answer. And so the answer is just 2.54 cubed, 16.39. 3 sig figs, 16.4. Now you don't have to write it out 3 times, because the alternative is to do this. Just 1.0 inches cubed. Write the linear conversion. So here's how you do it. This is the trick. Write the linear conversion. Cube, 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 cube. Just make sure you cube everything. You can't just cube. I mean, think about if I'm taking this if I've got 2a cubed? The answer is not 8a, right? You got to cube everything. It's 8a cubed. So make sure you cube everything. If I cube the units in this conversion factor, then I cube the numbers. And that'll give you the same result. So start with the linear conversion, and then just cube everything. Yes?
Would it be only 2 6 figs because of the first digits?
Oh, you're right, it would. Yeah, so that would be 16, sorry. 16 cubic centimeters. Now, you can use this with any kind of linear conversion. You can convert it into a cubic conversion. So let's look at a little bit more complex example. Let's say let's make it a little bit more complicated. What is the mass of air? Did we do this one yet?
No.
Of air in this room? What is the mass of air in this room? Now I have to give you some things here. I give you the density of air, which is about 1.2 grams per liter. That's the actual density of air. It's going to depend on temperature and pressure, but right now the air around us is about 1.2 grams per liter. So when I move my hand like this, I just moved it through about 1.2 grams of air. When you breathe in, you breathe in about 1.2 grams of air. So I don't know what your lung volume is, but maybe it's more than that. What is it? Do you know? So I gave you that. What else do we need to know to answer this? How big the room is, right? So let's estimate it. Here's a meter stick. What do you think? I know it's about 3 meters high. It's pretty close to 3 meters high. What about length and width? What do you think?
How long is the panel?
15.
I don't know. The panels look like they're about a meter, actually.
If the panels are a meter, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Should we do 1 quarter? They're like 10.
We'll say 10, and then how about it's about the same that way, right? So we'll say it's 10 by 10 by 3.
Factor in the fact that there's all this stuff in the room, right?
Yeah,
Like the counters and the
Let's not factor that in. Okay, 10 by 10 by 3 meters. So we got 300 cubic meters with 2 sig figs. All right, 300 cubic meters with 2 sig figs, we'll say. And that might be generous, but we'll say that's what it is, right? Make sense? Okay, now, what's the mass? And I'm given a volume, so that's where my density is going to come in, right? So I'm going to use the first technique that I showed you, using density as a conversion factor. But I also have to deal with something else, and that is liters and cubic meters. All right? Now, here's what we're going to use to do that. We're going to use this fact. This is an exact relationship. There's 1 cubic centimeter per milliliter. They are the same thing. That's actually the definition of a milliliter. All right? It's a cubic centimeter. Or actually, we would say a liter is a cubic decimeter. This is a liter right here. So we're going to start now. We don't want to start with the density because it's a ratio. And the reason you can start with a conversion factor, but you don't want to because it's too easy to get flipped over and end up. See, we don't know, maybe looking at this right away, am I going to want grams or liters in the numerator? Which am I going to want? Now, if you know that, actually I know I'm going to want the mass up there, so I could start with that. It's just more confusing. To me, it's simpler to start with this. Start with the quantity that they give you, all right? Which dictates what's in the denominator of the next factor. So automatically I know that I've got cubic meters in the denominator of the next factor here. But now is where I'm kind of stuck. Because I don't see meters up here anywhere, or cubic meters, except here. What I do see is this, centimeters, right? So, well, what if I could go to cubic centimeters? If I could convert to cubic centimeters from cubic meters, then I can get milliliters, and from milliliters, I could get liters. Follow? And then from liters, I could get grams, and that's what I'm looking for, right? So let's do that. And to do this, we're going to use our little trick here. I don't know how many cubic centimeters in a cubic meter, but I know there's 100 centimeters in a meter, right? And so cubit, 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 cubit. So there's 1,000,000 cubic centimeters in a cubic meter. 1,000,000. But think about it. Here's a meter stick, right? This is 100 centimeters long. So it's 100 times 100 times 100. That's 1,000,000. 10 squared, 10 squared, 10 squared, 10 to the 6th. Right? So now I'm in cubic centimeters. It's 300 million cubic centimeters in this room. 300 million. Change that to milliliters. 300 million milliliters. Change that to liters. $300,000 liters. $300,000 liters. That's the volume of this room approximately. Cubic meters gone. Cubic centimeters gone. Milliliters gone. Grams, 1.2 grams per liter. This is the air now, okay? This is the density. This is when we're, up until this point, we haven't even cared what substance we're talking about. We've just been calculating the volume of the room. Now is when we switch over and we start to think about what is this stuff, right? 1.2 grams of air. Let's go ahead and go to kilograms. I didn't say what in, but let's say in pounds again. We're pounds type of people, right? Thinking pounds still. So we'll go ahead and go to pounds. 2.2 pounds per kilogram. All right, so let's see. I've got 300. Whoops. 300 times 1,000,000 divided by 1,000. That's right here. Times 1.2 divided by 1,000 times 2.2. Is that right? Yeah, I suppose that's right. It seems a little low, but I guess we guessed lower on the volume, I think, this time than last time I did it. 792 pounds of air in this room. So, it's quite a bit. But that's what you can do with the factor label method. So it's got a lot of power for being able to do calculations like this. What's that? Well, even right now, it's just, right now there's that much air in this room. If you wanted to experience it, yeah, if you pumped it into a tank, then the tank would weigh 792 pounds. Not counting the steel in the tank. Yeah, so it's a lot of mass.
It's going to be complex in the test.
No, on the test we will keep it to about a maximum of 4 conversion factors. So this is a little bit over that. This is what, 6. So, but again, what would you need to know? This you would need to come up with on your own. This, this, this. Okay? You would be given the density and you'd be given this conversion to English units. And what is this? This is just centimeters to meters. So you know how many centimeters in a meter. This is a definition that you should know. 1 milliliter is 1 cubic centimeter. And then 1,000 milliliters per liter, 1,000 grams per kilogram. So this is really, it's like putting together a puzzle when you're actually not, you have to make the pieces yourself. Right? So it's like putting together a puzzle when you have to make the pieces yourself. Some of them are given to you. Some are not. You don't know which ones are not. And you have to make them up. So it's kind of fun like that. It's like a game. And it is kind of like, see, I think about it like a puzzle because look, it's got this kind of almost geometry to it where everything's lined up in a certain way, right? And you're basically, once you figure out the piece, here your puzzle pieces are always in this form. They always have a top and a bottom, right? And the top of one has to line up with the bottom of the other, right, in terms of units. So there is a kind of arrangement to it as you're going through this. You always know what's going to be in the next conversion factor on the bottom. You always know that, right? Let's try another type. This is the third kind of advanced method is conversion factors. So in other words, converting a fraction, one into another. So let's say something like this, convert the speed of light 3 times 10 to the 8th meters per second into miles per hour. Because that's what we think about speeds in terms of miles per hour, right? So let's convert meters per second into miles per hour. So what's the speed of light in miles per hour? You're going to have to be given a couple things here. I'm not going to give you seconds to hours. I'm going to expect you to come up with that. Yes? The last one? Yep. Yes. Yep. Right, it wasn't up there originally. I tacked that on at the end. I decided to go to pounds instead. Sorry. Well, hopefully I specify in the question. If I don't specify, then you just leave it whatever you want. Like if I just said mass, you would have been justified to just give me grams at the end. So I'm not going to give you seconds to hours. You should be able to figure that out. But we can see here that we've got two different length units. We have meters and miles. So in this case, I would give you in this problem, I would have to give you this one, 1.609 kilometers equals 1 mile. But that's all I would have to give you because you should know the meters to kilometers. Now, when you're approaching a problem like this, it's a good idea to write everything out. So write out what you're given, write out what you don't have, write down what you think you might need. Like in this case, if I was just starting this problem, I might write this. 3,600 seconds equals 1 hour. Now maybe you don't know that off the top of your head, and if you don't, then you could write 60 seconds is 1 minute, 60 minutes is 1 hour, right? You could write those down. What else would I write? I would probably write this. 1,000 meters is 1 kilometer. So see what I'm doing here is I'm writing down some possible puzzle pieces that might help me. And how did I pick those? Because I see my units here, and I'm asking myself, what do I know about those units? Meters, I know there's 1,000 meters in a kilometer, right? And it makes sense to write that down because he gave me 1.609 kilometers is 1 mile. Right? So I'm getting everything spread out in front of me so that I can start putting it together. Now this is the one case where you're going to actually start the calculation with a ratio. And it's because they're asking me to convert this ratio into another one. So in this case, they haven't given me just a straight quantity. They've given me a ratio. It's a speed. Convert this speed into other units. 3 times 10 to the 8th meters per second. Now, this is different than what we've been doing because there's 2 units I have to convert here. It's not just one. But it's really no more complicated because, or it's no more difficult because you just do one at a time. So let's start by converting meters into miles. So that's going to be the first step. Let's go meters into miles. That means I want meters in the denominator. Miles, nope, I can't go right to miles because I don't have a straight conversion between meters and miles. So I'll go to kilometers first. Again, make sure you don't switch these. It would be a very common mistake to write 1,000 kilometers over 1 meter. So you might want to check yourself on that when you're done. Look back, make sure you've got everything, the right numbers in there. This cancels meters. Now I have kilometers. So the next conversion factor is going to have kilometers down below. Now another thing you might want to do is conversion factors you've already used, get rid of them. You are never going to use the same conversion factor twice. Well, you could, but not in a problem like this. So get rid of it. You already used it. If I used it again, I'd be going backwards. So now I've got kilometers, and I have 1.609 kilometers and 1 mile in the numerator. And I have now taken care of my numerator. Now I've got miles in the numerator. So I'm done with that. I'm now going to take on the denominator. So I'm going to put seconds up here. You see that? What do I want to do? I want to cancel seconds, so I put seconds up here because seconds is in the denominator over here. So I put seconds in the top, and I want hours in the denominator, so I'm going to put hours down below. 3,600. Okay. Yes.
Does it matter if the mile and hours are crossed off, or can you still do that? Because like everything's crossed off except for 1 mile and 1 hour.
Yeah, well, see, what happens then is the miles, everything gets multiplied through, and you end up with miles and hours. And that's what we wanted, right? So we wanted to keep those. That's why we didn't cross them out. We didn't cancel them because we wanted to keep them. So what would this be? I've got 3 times 10 to the 8th divided by 1,000 divided by 1.609 times 3,600. Let's say 671 million. So, and I've got what, 2 sig figs, so 6.7 times 10 to the 8th. $670 million miles per hour. So those are kind of three more complex types of problems that you might have to deal with factor-label method. And they are using densities or speeds as conversion factors, converting cubic units, and converting conversion factors. So converting one rate or density or something into another. Questions on those 3?